Welcome back to Conceptual Physics at Delaware Tech, Chapter 4, Newton's second law of motion. So in this unit, we'll talk about how force causes acceleration. We'll talk about a special type of force called frictional force, or friction. We'll talk about weight and mass and how they differ. We'll talk about how mass, that is inertia, resists acceleration. We'll talk about Newton's second law of motion, which is expressed mathematically usually as F equals ma, force equals mass times acceleration, or acceleration equals force divided by mass. And it's good to keep both of those in mind. We'll talk about the difference between free fall and non-free fall. Free fall is when an object or a body drops from the sky and falls accelerating with the acceleration due to gravity completely. Where we don't even count the resistance due to air, something called drag or air resistance. Non-free fall is anything where the acceleration is a smaller rate than gravity would be because there is air resistance, because there is drag, friction due to air. So force causes acceleration. Acceleration depends on the net force, and just to remind you, net force is the sum of all the forces acting on a particular object, body, whatever. So if you sum up all the forces, that's what that sigma symbol is. It's the net force, the force sub net, is equal to the sum of all the forces. So they might be pointing in different directions, and you add up all the vectors, and whatever you get that's left over that's not zero, that's the net force on an object. And that will determine not just the net force, but the net acceleration in the same direction. So the force that we get is equal to the mass times acceleration, or the net acceleration is equal to the net force divided by the mass. So you add up all the forces, divide it by all the mass, and you'll get the acceleration in the same direction as the force. So acceleration is directly proportional and in the same direction as the net force. If you look at the formula A equals F over M, A is directly proportional to F in this formula. You can also see A is inversely, also called indirectly, proportional to the mass, because mass is in the denominator in the A equals F over M formula. So, and if you look at the left formula, F equals ma, you see the force is directly proportional to either the mass or the acceleration. So keep your proportions in mind so that you know when one thing goes up, the other will go up, or one thing goes down, and the other thing will go down, or if it's inversely proportional, one will go up, one will go down, or vice versa. So acceleration, the net acceleration, is proportional to the net force on that body, on that object. And so if you increase the acceleration of the object, you'll increase the net force on that object, and vice versa. So here's a quote. Consider a hockey puck at rest on ice. Hit the puck. That means apply a force. You're applying a force as you're striking the puck. The second you release the puck, it's no longer having a force acting on it, and it will just go in whatever the velocity it was when it left the stick that hit the puck. When the hockey stick is no longer pushing it, that is, when no unbalanced forces act on the puck, it moves at a constant velocity. So initially it's accelerated by the stick, and then it moves at a constant velocity. Apply another force by striking the puck again, and again the motion changes. Unbalanced forces, that is a non-zero net force, acting on an object cause the object to accelerate. And that's a quote from the book. It's important to note acceleration only occurs as long as the net force is still acting on the object. In other words, as the stick is contacting the puck, or a baseball bat is contacting the ball, or golf club is contacting the golf ball, that's when the force is being delivered. As soon as they stop touching, the force is no longer being delivered, and they just are released at whatever their final speed was after they accelerated. Friction. Friction is a type of force. It's a very specific type of force that resists movement, and it depends on the types of materials that are rubbing against one another and how much they're pressed against one another. So how much force is pushing them together and how bumpy their surfaces are. And it doesn't just have to be a solid on a solid. It could be a solid on liquid. Like you can have a boat having friction as it's going through the water. You can have a plane feeling friction as it's going through the air. Skydivers, as they're falling, they will feel the force of gravity pulling them down, but they will feel the air friction, the air resistance, also known as drag, pushing them back up. So friction comes in many forms. So in the terms of the solid on solid friction, it's due to the tiny surface bumps and stickiness of the atoms themselves between the two surfaces coming together. And if you look at a microscopic view, it's actually very bumpy, even on the smoothest surfaces. If you look with a good enough microscope, eventually you'll see the bumps and know why there's friction. They're basically getting stuck in the little holes as they move along. So here it's showing friction between a crate and a smooth wooden floor. It's going to be less than the friction between that and a rough wooden floor or rough floor of any type. So friction, the force of friction can occur A, with sliding objects, B, in water, C, in air, D, all of the above. And I think I just said friction can happen between solids and liquids, gases and gases if they're pushing against one another. So any forms of matter brushing against any other forms of matter will have a friction as a result. So it's all of the above. And that can happen either as the objects are stuck together at rest, there's a frictional force holding them in place, or even as they're moving. It does make it harder to move. You're going to need to apply more force to make the object move. And friction is always, always, always in the opposite direction of whatever the motion is. There might be other forces going on, but whatever direction motion is happening, it's the opposite of the direction that the force is going to be in. So remember, the force of friction is going to be in. Remember, friction is a force, it's a vector, it has a direction, it's always the opposite of motion. So if you push horizontally on your book and it doesn't move, then that means the frictional force between the book and the table is exactly equal to the push force that you've applied, the applied force. Friction can occur between any substances, I already said that. So even in water and air it can occur, and in those cases, we don't generally just call it friction, we call it drag or resistance. So here's a question for you. When Sanjay pushes a refrigerator across a kitchen floor at a constant speed, the second you see constant speed, red flags should go off in your head. Constant speed, net force is 0. The force of friction between the refrigerator and the floor is A, less than Sanjay's push, in other words, less than the applied force that Sanjay is giving, equal to Sanjay's applied force, equal and opposite to Sanjay's force, or more than Sanjay's force. Well, I just told you the clue about a constant speed. It means the net force is 0. So if friction is pushing against any place, any way that the applied force is pushing motion, and there's a constant speed, that means the net force is 0, so they must be exactly equal and opposite in direction. So constant speed means acceleration 0. It means that the net force is 0. Therefore, the applied force is exactly equal to the friction. Now you might say, well, wait a minute, if I push a little harder and it still doesn't move, how can that be? Well, the force of friction will keep increasing and increasing until the applied force is greater than the maximum friction force. Friction force can vary in force, just like normal forces can vary. They're resistant forces, so they'll get bigger and bigger until they're overcome, and then movement can occur after they're overcome. So here's an overcome situation. When Sanjay pushes a refrigerator across the kitchen floor at an increasing speed, that means there's a positive acceleration. The amount of friction between the refrigerator and the floor is A, less than Sanjay's push, B, equal to Sanjay's push, C, equal and opposite the push, D, more than Sanjay's push. Well, think about this. Sanjay is increasing the speed of the refrigerator. His force must be greater than the friction in order to have a net force. The net force is clearly no longer 0. It's something positive here in the direction Sanjay is pushing. So the refrigerator is no longer in mechanical equilibrium. It's before it was in static equilibrium because it was standing still, but it's increasing speed. If he had just started moving it at a constant speed, that would be dynamic equilibrium, but it says increasing speed, so there's an actual acceleration, a net acceleration, therefore there is a net force on it. That means he had to be pushing with more force than the friction force. Mass. So we talk about mass and weight in everyday life. We usually use the words interchangeably, but in physics, they don't mean the same thing. You'll occasionally hear me say weigh when I really mean mass, but I try to be good about distinguishing between the two. So mass is defined as the quantity of matter. And by using this definition in kind of a circular way, it means that all types of matter have mass. Mass is the substance that makes up matter, and it is a measurement of amount of that substance. It's the quantity of substance. We usually use kilograms as our unit of measure for mass, and it really is a measure of inertia. It's a measure of how hard it is, the sluggishness of that object to move when a force is being applied to it. The more mass, the more inertia, and they're somewhat synonymous terms. The more mass, the more inertia, the harder it is to accelerate it. Remember, F equals ma. If you increase m, that's a measure of the mass or inertia, you have to apply more force to get the same acceleration. So the more mass it is, the more acceleration, the harder it is to move. That's what inertia means. It literally means hard to move. It means sluggish. It means inactive. So compare kicking a bowling ball to kicking a soccer ball. One of those has a lot more mass. It has a lot more inertia. It's a lot harder to move with exactly the same force. More mass requires more force to accelerate it. Weight. Now, weight is a form of force. It is specifically the form of force due to the acceleration due to gravity. So we talk about gravity in terms of the acceleration due to gravity, that's 10 meters per second squared. We talk about the force due to gravity, that's either bringing two planets or large heavenly bodies together, or if we're talking about an object on Earth or a person on Earth, that's what we call weight. So weight is just a form of force. And we'll assume that the gravity is the same everywhere around the surface of the Earth. It's not quite, it varies around 9.8 meters per second squared for the purposes of this course. We're going to say 10 meters per second squared unless I tell you otherwise. And it is so the weight of an object depends both on the mass of the object and the gravity. Why? Because force equals mass times acceleration. The force in this case is weight, so weight equals mass times acceleration. But the acceleration is the acceleration due to gravity. So it's weight equals mass times the gravity's acceleration, what we call g. So F equals ma is exactly the same formula as weight, W equals mg. It's just a special version of that, a special case of F equals ma. W equals mg. Weight equals mass times the gravity acceleration. And that's the formula that's written right there. W equals mg is just a special case of Newton's second law, F equals ma. So mass, as I mentioned, is a kind of a measure of inertia of the object. The greater the inertia, the greater the mass, the greater the mass, the greater inertia. It is independent of gravity. Mass has nothing to do with gravity, and no matter where you are in space or Earth or another planet, if the amount of matter is the same, the amount of mass is the same, the amount of inertia is the same, no matter what the gravity is. It will still require a lot of force to stop a big, massive object, even in space, where there's no gravity at all. That may seem counterintuitive, but it's the case. The SI unit, the SI unit for mass is the kilogram. I mentioned this before. The metric unit is technically the gram. People use both, but for SI and what we'll use in this course, we'll focus on the kilogram as the unit. The imperial unit is something you've probably never seen before. So the SI unit of mass in the metric and SI, the SI unit and the metric unit of mass is frequently kilogram or some version of gram. And the SI unit of weight or force is Newton. We've already talked about that. The imperial unit of weight we've talked about is the pound, but the imperial unit of mass is something called the slug. And why do I have it in parentheses? Well, the abbreviation for slug is just slug. They don't have a shorter version of it. So weight is just the force due to gravity, and there are at least 3 different ways that people represent in formulas weight. W, force due to weight, F sub W, or the force due to gravity, F sub G. You'll see all versions, so don't let it throw you. They all mean exactly the same thing. They all mean M times G. So the metric unit or SI unit is the Newton for weight. We talked about that. The imperial unit is the pound. So pound and slug are the units in the imperial system. Kilograms and newtons are in the SI system. Okay, if the mass of an object is halved, another half means we cut it in half, then the weight of the object is A, halved, twice, depends on the location, none of the above. Well, F equals ma. F is proportional to m. Mass, force is proportional to mass. Weight is proportional to mass if there's gravity. So you half the mass, you're going to half the weight. Weight is directly proportional to mass. And you can see that from the formula. They're both in the numerator. The W on one side, the M on the other. So they're proportional. Cutting the mass in half will result in the weight being cut in half. Double one, you'll double the other. Triple one, you'll triple the other. Cut one into tenths, you'll cut the other into tenths. They do exactly the same thing. They move the same way as long as G is kept constant. So for example, an 80 kilogram weight, 80 kilogram mass would have a weight of 10 times that. Remember, gravity is about 10 meters per second squared, so you multiply it times the mass to get the weight or the force, 80 newtons, while a 4 kilogram mass would have a weight of only 40 newtons, 4 times 10 meters per second squared. So they follow together. Mass and weight will follow together as long as there is gravity present. And if it's Earth gravity, just multiply mass times 10 and you'll get the number of newtons. If you multiply 10 times the number of kilograms, you'll get the number of newtons. So weight equals mass times gravity, W equals mg. So weight and mass, we use them the same way in everyday conversation, but they're really very different to us. Mass is a more fundamental property than weight because mass is the substance of that matter, whereas weight is the effects of that matter by gravity. If there's no gravity, the weight will go to zero. If there's some gravity, the weight will be a little less, be low. If there's a lot of gravity, the weight will be very high. So the weight can vary quite a bit depending on the environment. So here's an example of a comparison of the mass versus weight on the moon versus Earth. Keeping in mind weight is W equals mg. The gravity on the moon is about 1/6 of the gravity on Earth. So the weight on Earth is 6 times the weight on the moon. The moon is 1/6 of the weight. So if a man or a woman an astronaut weighed 150 pounds on Earth, that's the same as about 667 newtons, okay, of weight. Their weight would be about 1/6 on the moon. So 667 newtons on Earth becomes 110 newtons on the moon. 150 pounds becomes 25 pounds on the moon. However, this is equivalent to a mass of 68 kilograms, and the mass isn't going anywhere when you go to the moon. You still have the same amount of matter in the astronaut, so they still have 68 kilograms whether they're on the moon, they're on the Earth, they're on a moon of Jupiter, they're deep space where there's no gravity, it's still the same mass. And in slugs, you can see that just is equivalent to 4.7 slugs. You can convert slugs to pounds by multiplying it by 32. You can convert kilograms to newtons by multiplying it by about 10. So a kilogram weighs, so a kilogram's mass, it weighs about 10 newtons on Earth because we multiply 10 meters per second squared times a kilogram to get 10 newtons in weight. It's really 9.8 or closer, but we're going to call it 10 for now. The relationship between kilograms and pounds. So that's a mass unit and a weight unit in a different system. But the fact is, people use kilograms and pounds in the United States all the time, so it's good to know that conversion. So 1 kilogram of mass on Earth is about 2.2 pounds of weight or force on Earth, and it's also about 9.8, or we'll round it to 10 newtons on Earth. 1 pound is about 4.45 newtons. I'm not going to ask you to memorize all of these. You should know that gravity is about 10 meters per second squared, and that's going to come up quite a bit and be helpful if you just remember that. So the metric units, if you follow these, of mass times acceleration equals force, or mass times gravity equals weight, it's the same thing. Mass is in kilograms, acceleration is mass per, meters per second squared. When you multiply them together, you get kilogram meter per second squared. Well, kilogram meter per second squared is exactly the definition of a newton. That is a newton. Remember, a newton is the weight or force due to 1 kilogram being accelerated to 1 meter per second squared. So kilogram meter per second squared is a newton. In imperial units, it works exactly the same way. Instead of kilograms and newtons, it's slugs and pounds. So it's slugs times an acceleration in feet per second squared. You get a slug foot per second squared. That's a very awkward sounding unit, but that happens to be what a pound is equal to. So if somebody gives you a number of slugs and they give you gravity is 32 feet per second squared, you just multiply how many slugs times the gravity of 32 feet per second squared, and you get how many pounds. Or you can divide the pounds by 32 and get the slugs. Okay, so when a string is pulled down slowly, well, let's look at this diagram first. You have a weight hanging from the ceiling. It's being held by a string, and then there's a second string below the weight being pulled by a person's hand. So the question says, when the string is pulled down slowly, the top string breaks. This best illustrates the blank. The weight of the ball, the mass of the ball, the volume of the ball, the density of the ball. Well, something you have to keep in mind here is, why is the top string breaking and not the bottom string if you're pulling it slowly? And this gets a little tricky, so try to do your best to keep up with this discussion here. It is the weight of the ball. So when you pull down slowly, the force you are giving on the bottom string gets transferred all the way through to the top string. If you go slowly, there's enough time for the top string to feel that tension too. There's enough time for the ball to slowly accelerate as you're putting force down on the ball. There's already the ball's weight pulling down and the tension is holding the ball up. But when you add extra tension of your hand on the bottom string, you're putting more tension, you're putting more effective weight on the whole system. And the top string is feeling the weight not just from your hand being transferred, but also from the ball. So the two of those forces together are going to be greater than the maximum tension of the top string, the maximum tension it can hold, and eventually the top string will just snap. And that's why you see the top string break if you pull it slowly. But if you pull it quickly, the bottom string breaks. And this best illustrates what? The weight, the mass, the volume, or the density. Well, in this case, you got something very different going on. When you pull it quickly, it's the mass that's important. And more technically, it's the inertia of the ball that's important. Because remember, you're yanking it fast. The ball has inertia. It has a laziness of motion, a sluggishness to respond to the force that you're giving it with that yank. There's not enough time for the force to be moving the ball or even the string above it. The ball has a certain amount of mass. It's hard to get it to accelerate. You have to add a lot of force. And if you do it quickly enough, there's not enough time for the ball to accelerate down and snap the top string. But Because of that laziness, because of that inertia in that ball, the force from the hand does get transferred to the bottom string very quickly. There's not enough time to accelerate the ball. It doesn't want to move. And as a result, the only thing that can move is the bottom string when you snap it. So as a result, it snaps. So here's a real life situation that you're already undoubtedly familiar with that it illustrates the exact same principle. You're in the bathroom. I won't get into details, but you're pulling off a piece of toilet paper. What happens when you yank quickly versus when you yank less quickly, gradually? Which way will get you a small piece of toilet paper off the roll? Well, when you yank quickly, it will pull close to you because the whole roll hasn't had time to feel the force and start spinning and releasing all the toilet paper. But if you pull a little slowly, the toilet paper is going to snap somewhere down the roll of toilet paper, and you'll end up with this giant piece of toilet paper coming off of your roll. So, in the case of pulling it quickly, the inertia of the roll is important, whereas if you pull it more gradually, the weight of the roll becomes more important. So, mass resists acceleration. Inertia resists acceleration when a force is applied. So, for a given force, in other words, you keep the force constant, F equals ma. Remember, we're keeping the force constant. Let's think about F equals ma rearranged so that the acceleration is equal to the force divided by the mass. So that means the acceleration is on one side of the formula and the mass is on the other in the denominator. If you cut the mass in half, the acceleration doubles. So we decrease the mass twofold, we increase the acceleration twofold. They have the opposite effects of each other. And that's because mass is inversely proportional to acceleration. Remember, mass equals force divided by acceleration. So acceleration is on the bottom. It's inversely proportional. And in fact, they're each inversely proportional to the other. You raise one by a certain factor, you'll decrease the other by the same factor. If we double the mass, the acceleration will be cut in half. If we triple the mass, the acceleration will be cut in thirds. If we do a tenfold increase in mass, we'll get a tenfold decrease in acceleration. We decrease the mass 50-fold, we'll increase the acceleration 50-fold if the force is made constant in all of these. So as long as the force is constant, increasing the mass or the acceleration will result in the other property decreasing. One goes up, one goes down, one goes down, one goes up. They are inversely proportional to one another. And you can see that just by writing the formula as m equals F over A. Anytime you're looking at a variable on one side of the equation, look at where it is on the other side of the equation. If it's on the top, it's proportional. If it's on the bottom, it's inversely proportional. If it's on the bottom squared, it's inversely proportional to the square of that. So you have to keep that in mind as well. And we'll see examples of that later in the semester. So Isaac Newton was the first person to make a connection between force and mass and how it relates to acceleration. And this is what led to his second law of motion. So the second law, also known as the law of acceleration, basically says the acceleration produced by a net force on an object is directly proportional to the net force. So that means acceleration goes up, net force goes up. Acceleration goes down, net force goes down. And it's in the same direction. If the force was this way, the acceleration is in that way. All right? So acceleration is proportional to force. This is the proportionality sign. Oh, by the way, in your textbook, they use a different symbol for proportionality. They use the squiggle line that usually means approximately equal to for proportionality. I've never seen that in any other textbook, but just be aware that that doesn't mean that A is approximately equal to F. It means that A is proportional to F, if you see that in the textbook. But A is also inversely proportional to M. So acceleration goes up when the mass is down. When the mass is down, or when the mass is up, the acceleration will go down for a given force. So whichever two letters you're looking at, you keep the other letter constant. When you put these two together, it says that the acceleration is proportional to the force. That means they're both in the numerator on each side of the equation. And acceleration is inversely proportional to the mass. That means mass is on the bottom of the other side of the equation. You end up with acceleration equals force divided by mass. Rearranging that, it's F equals ma. Most people remember this as F equals ma, but you will find that actually it's almost more important to remember A equals F over m. The acceleration, the net acceleration that happens on an object is equal to the net force, the sum of all the forces, divided by the mass of whatever you're interested in. That will give the net acceleration. F over m equals A. So net acceleration equals net force over the mass. If the net force acting on the object is doubled, the acceleration will be doubled. You can see in this formula, they're both in the numerator, so they both will act in the same way. They both go up or they'll both go down by the same factor. You'll multiply them both by the same number or divide them both by the same number. Don't ever add or subtract in these cases. So if the mass is doubled, remember mass is inversely proportional, the mass is doubled, the acceleration will be halved. I twofold increase the mass, I twofold decrease the acceleration. So here are a number of examples here where we've got a mass and we've got a force and we're doubling the mass or tripling the mass or doubling the force, and we want to see what happens to the acceleration. Remember, acceleration is force divided by mass. Then total force, the net force, the sum of the forces divided by the mass. So we have these three cases here, and in the first case, it's our standard case. We have a force F and we have a mass m. F divided by m is our acceleration, and that'll be our standard acceleration. Now we'll play with different versions of this. So in number 2, we're doubling the force. So now it's 2F divided by 1m. We didn't change the mass. So now we'll get an acceleration that's twice as big as in the first situation. It's 2F over m's. So it's 2 accelerated. It's twice the acceleration. So double the force, we get double the acceleration. And this is the way you can quickly analyze. You double a number and you see how it affects the final formula product. Twice the force and twice the mass. So now we're taking 2F, dividing it by 2m. Well, that's just F over m. The 2's cancel out, and F over m in example 1 is just our plane acceleration, our A. So that's the same acceleration if we doubled both the force and the mass. Here are 3 more cases. In number 4, we've got a force accelerating the mass, so this is the same case as number 1. In number 5, the same force, but now we have twice the number of bricks, so double the mass. The same force, double the mass, so F divided by 2m is half of the acceleration that we got in cases 1 and 4. Right? It's 1/2 the acceleration, 1/2 A of the original A. And in situation 6, we've got 3 masses, 3 times the mass. So it's the same force divided by 3 masses. Well, that's 1/3 of the F over ma that we got in the first situation. So it's 1/3 of the original force. So you can think of it this way, or you can think of it in terms of proportionality. We double the force, we'll double the acceleration. We double the mass, we'll cut the acceleration in half. We triple the mass, we'll cut the acceleration in thirds. We double the force, which will bring up the acceleration, and double the mass, which will bring down the acceleration. If they're both doubled, will have no effect on the acceleration in case 3 that's shown here in the bottom left. So consider a cart pushed along a track with a certain force. If the force remains constant, force is constant, while the mass is decreased to half. So we're cutting the mass in half. F is the same, m is now 1/2 m. The resulting acceleration of the cart remains the same, halves, doubles, or changes unpredictably. Well, what are we doing? We're cutting the mass in half. We're making it less mass with the same force. We have the same force but less inertia to push. It's easier to push, and therefore our acceleration will be double with half the mass. Acceleration is force over mass. It's inversely proportional to mass. Change the mass twofold down, we will change the acceleration twofold up. And you can do that mathematically, or you can just think logically like I just said. If the mass is being decreased twofold, the acceleration will be increased twofold. And that's just saying the same thing. Okay, push the cart along the track with twice as much force, 2F, acts on it. If the acceleration remains the same, so A is the same, what could easily account for this odd result? So how could you get the original acceleration if you double force? Well, A, the mass of the cart was doubled when the force was doubled. B, the cart experiences a force that it didn't before. C, the track is not level. D, friction reversed direction. Well, I think we've already seen in one of the examples that one way to do that is just double the mass. When you double the force, you will get exactly the same acceleration. A equals F over M. If you double F and double M, the two twos will cancel out. And as a result, you get 2F over 2M. That's the same thing as F over M. That's the original acceleration A. So there's no effect on it. Free fall. Let's talk about free fall. What is free fall? Free fall is when you are falling or an object is falling and the acceleration of the fall, A, is exactly gravity, G. So acceleration is G, exactly G, 10 meters per second squared, approximately 10 meters per second squared, 10 meters per second. It increases speed by 10 meters per second every second it's falling. And that is free fall. In other words, we will assume free fall if I say that the air resistance is negligible. We're not going to worry about the friction of air slowing gravity down, okay, slowing the fall from gravity down. This is free fall. Free fall is always where the acceleration is the same as G. And Newton's law provides an explanation for equal accelerations of free-falling masses, objects of different masses, of varying masses. So acceleration of falling is only equal to gravity when the air resistance is negligible. So right now we're gonna assume there's no air resistance, like it was in a vacuum. Acceleration will depend on force. In this case, the force is the same as the weight. A falling object is falling. The force of the object falling is its weight. It's m times a, or m times g in this case. M times g is the weight. So it depends on the force, which in turn depends on the mass, which is a measure of inertia. So if we have the greater the mass of the object, the greater the force. They move with exactly the same acceleration if they're in free fall with no air, no air resistance. But they have different masses, and therefore they have different weights, and different weights means different forces pulling them down, different gravitational forces. That's what weight is, gravitational force pulling an object down. But the reason why they have the same acceleration down, the same acceleration due to gravity, is because double the force is twice as much when you have twice as much mass. 2F divided by 2M is still F over M. The twos cancel out and you still end up with G. Triple the mass and you let it fall, it will fall with triple the force. Triple force divided by triple mass is still G. It doesn't matter how big the mass is, the objects will all fall with the same rate of falling faster and faster, the same G, the same acceleration. They'll have different masses. They'll have different weights. Different weights means they'll have different forces, but they will have exactly the same acceleration as long as there's no air. So when you have these two objects of very different masses, the forces will increase proportionally with the masses. Greater the mass, greater the inertia, greater the force required to move that mass, to move that inertia with the same acceleration. And when you divide double force by double mass, you end up with the same force divided by mass as the other object, and that gives you the same acceleration due to gravity, or G. So the acceleration is exactly the same. They both fall with gravity about 10 meters per second squared. And here's the more precise number just to remind you. Okay, so at one instance, an object in free fall means no air resistance, has a speed of 40 meters per second. So that's 1 moment in time it's falling, it's at 40 meters per second. 1 second later, its speed is about, also 40, 45 meters per second, 50 meters per second, none of the above. Well, remember, gravity, 10 meters per second per second. It literally means that every second it will increase by another 10 meters per second. That's what 10 meters per second or 10 meters per second squared means. So the answer is 50 meters per second. And if we waited another second, it would get to 60. Waited another second, it would get to 70 meters per second. If we went back in time from the 40, it would be 30 meters per second 1 second earlier. If we went back in time 4 seconds, that would be when the object first dropped and it had no velocity, 0 meters per second. So we assume the object's falling downward. We assume gravity is about 10 meters per second squared, or 10 meters per second, and we just add 10 meters per second of fall. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest. So they're starting at 0 velocity. We drop them. We're going to assume negligible air resistance. That means free fall. That means A equals G. The acceleration of the heavier ball will be less, the same, more, undetermined. Well, if there's no air resistance, all objects will fall at the same rate of acceleration, G, 10 meters per second squared. Doubling the mass will double the force, but the acceleration will be exactly the same. Here's another one. 5 kilogram ball and a 10 kilogram iron ball are dropped from rest. Again, negligible air resistance. When the free falling 5 kilogram ball reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram ball is less than 10, the same as 10, more than 10, we have no idea. Well, I think I just said, if they're both in environments where we don't care about air resistance, they will fall with exactly the same acceleration no matter how massive, how heavy they are. So it's going to be the same 10 meters per second squared unless there's air resistance. So in free fall, everything falls the same rate, 10 meters per second per second. Objects of different mass will fall together as long as there's no significant air resistance. So when an object falls downward through the air, it experiences its weight. And we have lots of ways to express weight. I'm just reminding you, sometimes we use W. Later on, when we talk about work, we use W for work, so don't confuse those two. We use force due to gravity, force due to weight, and it's calculated as mass times gravity, the gravity acceleration, so mg. We also talk about air resistance. So now we're talking about non-free fall. When the free fall is not as fast as gravity would pull you down in an increasing rate. And that could be slower than gravity, but still accelerating, or it could be so much that gravity stops accelerating entirely and they just fall at a constant velocity. We'll talk about that in a second. So air drag, also known as air resistance, we sometimes will abbreviate it as F sub resistance, F sub drag, or R. In this textbook, we use R. I'll try to keep R most of the time. So you can have R in air. You can also have it in water, but we're talking about in air right now. So non-free fall occurs when the acceleration of the falling is less than standard gravity. That is, air resistance is not negligible. Air resistance always is in the opposite direction of the motion. If you're falling, it's pointing up because you're falling down. If you're going across, there's air resistance going against you. It's a form of friction, so it's always against your motion. So air resistance is actually dependent on a number of things, and the calculation is actually fairly complicated. We're not going to get into it. We'll just give you a value of R if we talk about R for the resistance, the drag. Don't worry about calculating, but it is dependent on how fast the object's going. The faster the object's falling, the more resistance there will be from air because the air is hitting it harder and more friction with it. It also depends on how much surface area is there. A big, broad object like a fat ball will have more air resistance than an arrow that's just pointing and diving right through the air, cutting the air. Okay, so compare the air resistance when you stick your hand out in a moving car. How does it change when you turn your hand? If you turn your hand this way, or if you turn it right into the air, you'll feel a giant difference. Your hand has the same mass. The air is not changing speed. But you can feel the difference in air resistance just by showing it more surface area. You can also find it when you speed up the car. You'll get more air resistance. So, non-free fall. When the object is moving fast enough, the force of gravity can equal the air resistance. So if you fall long enough and accelerate fast enough through say skydiving before you put out your parachute, or even after you put out your parachute, your weight will be coming down. That's the force down. And if you fall far enough, there's going to be enough air resistance getting greater and greater and greater as you're speeding up. Remember, it's dependent on how fast you're going. As you speed up, the air resistance will increase, and eventually the air resistance force up will be exactly the same as the weight of your body going down. And when that happens, there's no net force. Doesn't mean you're not moving. You're moving really fast, but you're no longer accelerating. And that's because the object just can't push enough air out of the way. And that's true if you're falling without a parachute for a long distance. Eventually you'll come to a velocity that you won't increase anymore. If you're wearing a parachute, that velocity will happen a lot faster at a lot safer speed. And that's why we use parachutes, to create so much air resistance that it stops the acceleration due to gravity. The force up from the air resistance on the parachute is exactly equal to your weight down of your weight with you in the parachute. So the net force is zero, the net acceleration is zero. The velocity doesn't change. It could be really fast. Even with a parachute, it's going to be somewhat fast. But without a parachute, it is extremely fast. And we call that velocity, that top speed, we call that terminal speed. If we give it a vector and make it point down, it's terminal velocity. So it's the speed that occurs when the acceleration terminates, when there's no more acceleration. It gets slower and slower until you're just falling without speeding up anymore. And that's when the force up, the resistance up, is equal to the weight down. It's when the net force is zero. So terminal velocity is the same thing. It just includes a direction typically pointing down, because that's the direction we fall if we're skydiving. So a skydiver jumps from a plane. Weight is the only force until air resistance kicks in. And as the speed builds up, the air resistance will build up, and the net force will be reduced, and the acceleration will be reduced. And if it's reduced long enough, you'll reduce the acceleration to zero, the net force to zero, and then you'll hit terminal velocity. And that's what we call it when the net force is zero, when the net acceleration is zero, and the velocity is constant. Could be big, but it's constant. So that's when a skydiver reaches terminal velocity and continues to fall at a constant speed. So when a falling object weighing 20 newtons encounters 5 newtons of air resistance pointing up. So we're just going to tell you the resistance is 5 newtons pointing up of force. Remember, resistance is a force, and the weight is a force going down. The acceleration of the fall is what? Less than g, more than g, or terminated. Well, terminated means the acceleration is zero, right? So you have a weight 20 newtons down. You have a force pushing up 5 newtons. That's a net force coming down of 15 newtons. Well, 15 newtons of force, your mass didn't change, but your net force changed. So it's no longer the original F divided by the original M. It's a smaller F divided by the original M, and therefore your acceleration is no longer g. It is less than g. You will slow down your acceleration. The acceleration of free fall is always less than g, always, because there's air resistance providing a counter force. So if you wanted to actually calculate this, you can realize the net force on the person is the weight minus the resistance, so that's 15 newtons of force downward. But remember, they weigh 20 newtons. 20 newtons divided by 10, the normal gravity, gives you 2 kilograms of mass. Well, this is an object, not a person. So this object must have a mass of 2 kilograms. That we know that before it was dropped. So 2 kilograms with 20 newtons of weight, well, that's 10 meters per second squared. That's normal G. But 15 newtons divided by 2 kilograms of mass, that's only 7.5 meters per second squared, or 75% of G. So it's less than 1 G. What if it's a person, a 500 Newton person? This is actually not an outrageous weight. 500 newtons is about 112 pounds. If that person was to fall at terminal velocity, you see terminal velocity, you know there's no net force. The resistance has to be exactly equal to their weight. So 500 Newton person falling, less than 500, 500, more than 500, impossible to tell. Well, the factor of terminal velocity tells you it has to be exactly 500. The net force and the net acceleration are 0. The two forces must be exactly equal to one another. And therefore, they're both equal to 500 newtons, but in opposite directions. Skydiver falls faster and faster through the air. The force due to air resistance increases, decreases, remains constant, impossible to tell. Well, if they're moving faster and faster, they're hitting the air faster and faster. So there's more resistance against them. This is what we were talking about before, where the force of air resistance will increase as you're moving faster and faster through that air. So as a result, we find that the air resistance increases. As the speed increases, there's more drag on the skydiver. It's building up. There's more air pushing past this individual as they're dropping down through the sky. And the net force is reduced because of this air resistance. Eventually, if they fall far enough, the air resistance will build up so that the force of the air resistance will be exactly equal to their weight, and that's when they hit terminal velocity. And they'll just fall fast. And that can be very fast. That might be without a parachute. That could be 120 to 170 miles per hour, depending on what the shape and size of the person is. So as the skydiver falls faster and faster through the air, the net force, A, increases, B, decreases, C, remains constant, D is impossible to determine. Well, we know that as they fall faster and faster through the air resistance builds up. The R value increases while their weight is still the same, so the net force will get smaller and smaller until the two equalize. So, as you might expect from what we've been talking about, the net force will in fact decrease. So as the falling speed increases, the air resistance builds up, the net force is reduced due to increased air resistance. And eventually, the two equal each other, the net force is 0, and that's terminal velocity. Okay, as the skydiver falls faster and faster through the air, her acceleration increases, decreases, remains constant, is impossible to determine. Well, remember, her net force is getting smaller and smaller. Whatever happens to the net force happens to the net acceleration. So if the net force is getting smaller and smaller, the net acceleration is getting smaller and smaller too, due to the increased air resistance. Force decreases, the acceleration decreases. And eventually they'll be equalized, so the net force will become 0, the net acceleration will become 0, and that's terminal velocity. So if we had asked this question, this last question first instead of at the end of this series of questions, how well do you think you do? Just think about that for a second. I'm not sure if I would have done that well if I had never seen this before. So it's okay to admit that you might have been a little puzzled, but hopefully now you know exactly what's going on. All right, so here's a slightly different situation. Consider a heavier and a lighter person jumping together at the same time with the same size parachutes from the same altitude. So everything's the same except one's heavier than the other. Who reaches the ground first? Well, if there was no air, I think we all know that the answer is they'd reach the ground at exactly the same time. No air resistance, that's free fall. They'd both be coming down with the force of gravity. In fact, the parachutes wouldn't work at all. Parachutes only work because of air resistance. So parachutes wouldn't help them if they're falling through a vacuum or falling on a planet that didn't have an atmosphere. That they only work if there's something to resist against the large surface area of the parachute. But this is a case where there is air resistance, and we know that as they're falling, they're going to be getting faster and faster, and as they get faster and faster, there's going to be more and more air resistance till eventually the air resistance equals their weight. Well, which one will the air resistance hit the weight of the person first? Well, the air resistance will eventually equal the one of the lighter person faster than the heavier person. So it's the heavier person will end up moving. They will take longer to reach terminal velocity. They're going to still be accelerating down while the lighter person may have stopped accelerating. They're moving fast, but the other one is moving faster and increasing their speed. So the heavier person will arrive to the ground faster. So they both have the exact same drag force because they both have the same parachute. The heavier person has a greater weight, a greater downward force. So there has to be more air resistance, more drag, more R, for the heavier person to reach terminal velocity. So the lighter person will hit terminal velocity earlier, and they will stop speeding up. They'll just be coming down at a constant, slower speed because they have a parachute. The heavier person, it'll take longer for that to happen. So let's talk about a coin and a feather. We looked at a video before. This is just a graphic representation of a coin, metal chunk, and a feather, something that has lots of air resistance. And when you drop this in a tube that's filled with air, the feather will reach terminal velocity very quickly. It's hard to think about feathers reaching terminal velocity. We think about skydivers reaching terminal velocity or some object dropped from the sky. But the fact is, a feather has so much surface area and so little weight that it doesn't take much air resistance to keep it from accelerating down. And as a result, the feather's rate falling down gets slower and slower, and to the point where it just is a constant speed coming down. It's at terminal velocity. Well, a coin in a tube, that's just not going to happen. There's not enough space for the coin to fall far enough to build up enough air resistance that it would equal the weight of the coin. So the coin will come down in near free fall, and the feather will come down definitely in non-free fall as a result. So the coins will fall very quickly with an acceleration. The air resistance won't build up on it in such a short distance, so it'll hit the bottom very quickly, and the feather will take much longer. So when the coin and the feather are dropped after the air has been removed by an air pump, what will happen? Well, I showed you a video of that. You should already know the answer. A, the feather hits the bottom first. B, the coin hits the bottom first. C, they drop together side by side. D, not enough information. Well, I think you know, without air resistance, we've talked about this, every object will fall with exactly the same acceleration. The acceleration due to gravity, G, about 10 meters per second per second. So they fall side by side. There's no drag force. The resistance is zero. They both are in free fall. Weight does not affect the acceleration if air resistance is negligible. But you put the coin and the feather in a vacuum tube with no air in it. No air, no air resistance. Only gravity is the force on each of these. They will come down at exactly the same fast and accelerating speed. They will both come down fast, and they will both get faster as they fall with an acceleration due to gravity, G, 10 meters per second per second. And with that, that's the end of the unit. Thank you very much.